Good morning, everyone. I hope that you're all having a wonderful Tuesday morning, and hopefully the week is not treating you too badly, considering it's the last week of the semester, and uh, and hopefully things are going smoothly in terms of all the assessments and all that that I know for the informatics deliverables and everything else, and we can wrap things up for the semester. So, for before I begin, I just would like to mention I have a few announcements. Um, I'll get through each and every one of them. Um, I will be, uh, because it's a lot of announcements, I'll try to compile a document and everything that you all get for for further clarity, 'cause the large portion of it relates to the exam with the proctorio and all that. So the first announcement is there's not going to be a practical 11. With everything going on, there's it's just not enough time. I have not had a chance to set it. So I've got a half, not even half, maybe a quarter set, and it's not going to happen by Thursday. So with all the marking, I'd rather prefer marking everything on time than having that done. In terms of bonus practicals and everything, it doesn't look like it so far, but I have tried to add something which I'll speak about in a moment. So the 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 bulk portion of the announcements is of course related to the exam with Proctorio. So I know a lot of you, there's a lot of uncertainty with regards to how the format of the exam is going to be. And, a lot of you have lingering questions. And we spoke to a few students yesterday, to sort of air some of these sort of concerns. And, you can ask them that they spoke with many of the higher levels of the university, and so a lot of the stuff just doesn't come from me or from nowhere. It's actually a lot of it is you know that's they've prescribed a lot of this. So the first thing is naturally um, it will be a proctor exam, and you'll see with informatics. Mr. Moodley will tell you about with all of this, and you have a mock test with him on Friday. And the other thing, of course, that you need to be aware of is that you need a device with a camera and a microphone in order to do the assessment. And if you haven't had a chance to have a look on Discord and all that, you can get a device on loan. I have been doing this for people that have asked, but I thought maybe some of you have didn't know about this, but you can get a device on loan. Um, you would normally email uhelp@uj.ac.za, but I've been helping a lot of students get them quicker before the exam. And I'm not sure if I can still do that today, but I'll see if I can try where they're trying to get it to them before the informatics exam. So there are some T's and C's. For example, there's a 4,500 sort of um, charge put onto your account. The idea is if you're a NSFA student, the 4-5 goes to student finance, and you have this. If you're not a NSFA student, you get a 2020 loan device where they add 4-5 to your account, and then when you return the device, they give you back that 4,500 or it gets deducted on the account itself. So if this is you, please do do something about it. And you know, in terms of getting around this for the duration of the year, because the rest of the year is going to be online, and if you're having issues now, I would strongly recommend that you make a plan to actually get a device that's capable of doing this, because you'll see as we go through, many of the assessments are going to be proctored. It's not just so next semester you'll see a lot more of proctorio and and monitoring and all that. So just to sort of give you a heads up, that's what's going to happen. The other thing I also want to do today is that because it's a proctored exam, there's no need for any funny settings that they wanted to have. So it's either when the exam is proctored, that means there's no separate questions. It's just all the questions are shown all in one go with one timer for the whole assessment, and you could upload. There'll be a file response right at the bottom, and you upload the handwritten version if that's what you want to do. There's no obligation to sort of there's because of this. I'm allowed to do things like making sure there's no there will be, because all the questions are shown in one go. That means there is no setting for backtracking or anything. It just shows everything all in one go, and you can choose which question you want to do. That means that because this is the case, there's no need for stuff like that. There's no need for separate questions and different assessments or timers or weird, funny things like that. That's just not going to happen. And it's just one assessment with the full duration of the time, and then the questions and the file response. So there'll be a file response for certain questions, but then there's a final file response as well that you can use to upload the whole thing if you want. And then Eve will be used as the second place you submit your exam as a backup. So the idea is that the Blackboard is the primary way of doing the assessment, but your submission must be submitted on both sides. That's how it's going to go down. So um, what what I also want to say is that I thought, just to sort of put your mind at ease, is that we're going to do a very, very short mock test that's going to be the same format as the exam during the practical session on Thursday, to sort of see what it's to do this. And maybe you'll see that it's actually not that bad for all of this. Um, you know, I want to stress that when it comes to all of this, that you need to understand is that for this particular assessment, this mark assessment, there's not going to be any information, um, you know, distributed anywhere or anything like that. It is because I, Mr. Malulek and I are the only ones that are going to see what is submitted, and I just want to sort of alleviate any concerns. You're not going to be kicked off any assessment when you do it. Remember, if you get flagged, a lot of you refer to when do I get flagged and all that. What you need to understand is that you are always given the opportunity to write the full test and everything like that, and only after the fact does is the report sent out that there were certain discrepancies or flagged certain students, and then we would review very briefly and see whether there's a valid reason, or or see, okay, no, it just seems like it's nothing, and you carry on. There's nothing else that happens. It's not some elaborate um we're not going to be doing anything else at all, and you're not kicked off during the assessment and everything like that. In case you're wondering, um, you know, every single exam at third year level, exit level, is moderated by a person outside of the university. Every exam inside, or every semester test, is moderated internally. So, there's not going to be any concerns like mistakes, weird things happening here and there, and all that. And, in terms of all of this coming together, and getting the document that outlines all of this, and I'm even adding in the document some suggestions in terms of how to go how to get through everything in terms of so for example, how to get through tips in the settings and all the other stuff I'm going to be disseminating, and hopefully I'll get it to you by Thursday, so you can see immediately what some of the do's and don'ts are, and and all that. And this document will hopefully help you with understanding a lot of this stuff. So the exam is open book. That's correct. Be able to open up a new tab, go to Eve or another place and all that. Um, the only reason why we monitor is for things like communication outside of the scope of what's that's against the academic regulations. Good morning. Would multiple submissions be allowed? And you take the latest submission. So on Blackboard, there's only for file responses, there's only one file allowed to upload per question. So there's no multiple submissions on Blackboard, but naturally you would see on Eve that multiple submissions are allowed. So I want to say that on Blackboard, that's not what you can't do that on Blackboard. But on the second place for Eve, when you submit your submission the second time, that's you can do that. That's not a problem. The latest one. Meaning you can answer some questions on Blackboard and then submit some on Eve like during. So ideally, you want to have two places where you submitted everything. So you'll see there's going to be an area that is, um, as I said, there's a file response for any file. So any question that involves drawings. So there's going to be file responses for each of them. And then what's going to happen is right at the end, there's a file response if there's a spot that you want to use for the whole assessment. Let's you wrote them down. Want to put it in there for argument's sake, you can do that too. Because remember, everything is shown in one go, so you can just do that. And of course, naturally, when we mark your exam, we will look at your Blackboard submission and your submission. So this you're supposed to submit it in both places. So if you were having problems with Blackboard or something like that, there will always be an E version that we can use to mark. Will the exam be on everything until red black trees, or is there more? So red black trees, there is one more lecture, and that's graphs. So a lot of the stuff that you've already covered, like what graphs and all that, I do go over as a brief primer for some of the stuff because I see that a lot of you are still struggling with graphs. So there's going to be another lecture that covers this. Um, and it's just to make sure that you fully understand what's actually happening, and things will make more sense in terms of the implementation of graphs. And you'll see that everything we've been doing is actually graphs. It's just I'm more explicit about formats and representations and traversals and things like that that I've not been covered thus far. We'll be allowed to type out answers for certain questions and submit PDFs for questions that require diagrams. Yes, you can do that. On Proctor, are we allowed to use one monitor? So will it be a problem if we take pictures with our phone and upload on our PC since our phones are not monitored? That's perfectly fine. It's I'll try and be explicit in terms about the settings that I'm going to be using for do's and don'ts so that things are more clear. Naturally, you're going to be uploading files. It's just how it works. So um, you know anything that's a legitimate use for what you're supposed to be doing during your assessment is fine. We're not going to hinder you in any way to do that. So please do keep that in mind. The rule says use one device when we write on book, then we have to use the other device to scan and upload. Um, I'll clear that out in the document. So what if your microphone is on a headset? It doesn't matter where the microphone is as long as it's there. That's how it works. So in fact, I'm talking to you on a microphone on my head right now, on my headset, not on my head. So there should be no problems with that. Okay. Okay. So, as I mentioned before, I'd like to wrap things up for the semester. So, during the course of today and tomorrow, I should be able to get through everything in terms of red black trees and that last graph lecture. And on Thursday, one of the things that I want to highlight is that when it comes to on Thursday itself, I would like to do some revision and tips for the exam so that things go a lot better. Okay. Okay, so let's get on to red black trees. Now, one of the things that I wanted to mention is that when you do 2,4 trees, you'll realize that it seems a lot very overly complex to have multiple entries inside of one node. And many people argue that by having multiple entries inside of one node, that is the primary reason why 2,4 trees are considered very complex. So, a way of alleviating this is that someone came up with a representation of a 2,4 tree as a red-black tree and behaves in the same way. So the only difference is it's still a binary search tree, but it achieves exactly the same as a 2,4 tree. So this makes things very, very interesting because how they achieve this is by having some notion of color, where there's two colors that represent some sort of structural components. So what the two colors, and we normally refer to them as red-black trees, then form the fundamental basis of many, many cache-based systems in computer science. And you don't even know this, but there's a lot of red black tree based anything related to efficient assertion or indexing and all that. Um, you know, and a lot of them use red black trees, and you know they scale until a point. And in aspects like big data and all that, they moved away from. Uh, they don't scale very well on the very very high end. And the reason why I'm going to be doing graphs with you, by the way, is because nowadays they've moved back to something that was used in the past, where we don't have a relational databases and all that, and we have more graph-based stuff, which scales enormously better than, for example, some of these red-black trees. And that's one of the reasons why I'd like to specifically address, because I know a lot of you are going to be going into that area, or you should at least know the basics of that area. So one day when you specialize perhaps in honors in a specific topic like or AI, um, clearly by when it comes to other areas, or like in my field like computer vision and big data and data science and a whole bunch of other stuff that are related to that. And hopefully, if I would urge you to, of course, at this stage, to consider at least uh, doing an honors, because I thought this is the last week, and it's the last week you're going to see until, if you do honors, then you'll see me in biometrics and big data and other things. But um, I would definitely urge you to stay on that extra year for honors, because remember, an undergrad is all about how to teach you how to program in a sense that you can create systems from a software engineering point of view. At honors, you specialize in specific areas that are more focused in some of the big areas in our domain. So for example, if something like security, cybersecurity is a big thing. There's a 500,000 people in the US, or 500,000 jobs in the US in cybersecurity alone. There's a recent study that has shown the skill deficit is humongous. And even in South Africa, it's like an instant job if you can do something like that. The other area, of course, is artificial intelligence and all different variations and all that, and a lot of other web-based, topics, computing and all that, and in other areas where you didn't really think that computer science is actually involved in there, but it is, like digital forensics and all sorts of other things. And at the very least, go look at the honors brochure to see what specifically you can specialize in. because a lot of people in specific jobs only take people that have specialized in that particular area. Um, what are the requirements for honors? You need to have a 65 for one of your majors. So if it's for 65% for computer science, an average of that, or a average of 65% for informatics, then of course this naturally allows you to either register for one of the degrees of honors. But let me tell you a secret: there's no material difference between them, because you'll always have, if you're going to be doing full time, there's always 5 modules in the first semester and 4 modules in the second semester. Or if you're part time, that's split over 2 years. Um, in terms of honors applications, you'll probably hear more of that in next semester. So you'll see that during the course of next semester, um, you'll be able to they'll give lots and lots of announcements for all that stuff. But next semester, in case you didn't know, is given by Dr. Dutoy and Mr. Mugnall. So that's everything. Covered it. Okay, let's get back onto red black trees. Should we go for part time? Well, it depends on you. If you can get it out of the way, get it out of the way. Um, and I was quite lucky because I got a bursary that's a full ride from undergrad, because my parents couldn't afford to send me to university. Just never mind school, but bursary is what got me here. So if you can get there and if you do well, then things will go really well for you. And what I wanted to say is that honors is probably going to be difficult. And in fact, when I look back, it's probably one of the most difficult years I've ever done. It was probably more difficult than my master's and my PhD and all that. And I tell you why. Because if you're doing it in one go, you learn there's so much new stuff that you get introduced to. You realize that there's a lot more to software development than what you've learned so far. And what you also need to understand is that there's a lot more out there, and you don't really know what's out there until you do it. And it might be easy to say I'm going to become a cybersecurity expert and then go beyond my way. But when you start doing it and saying, well, actually, this is not what's for me. Maybe I should be doing things in biometrics and or computer vision, that's part of biometrics and stuff like that. And that's more interesting to you. Don't you think you should figure that out in that year rather than in your career over a longer period of time? That's just how it is. Okay, so so when it comes to the bursaries and stuff like that, merit bursaries, and well, you can apply for other bursaries on the side as well. There's a lot of honors bursaries outside, but you contact finance for that. So I'm trying to get through the content. So I'll try and answer questions and all that stuff. Yes, you do have to write the entrance exam. Every person writes the entrance exam. It's the equivalent of a first year assessment, like your informatics second semester test. Somewhere there and thereabout, there's a question on your computer science 3A stuff, and and then that's your or there might also be a question on informatics 2 for websites. Those three things are typically what we ask. So each of us submit a section for that honors entrance exam, and it's very easy to get through. Okay, so red black trees. So red black trees are binary search trees. So what this means is that the same ordering information like less go left, more go right applies. It is in many ways very much like any other binary search tree, but the rules that are applicable for restructuring are a little bit more. You'll see in a moment by how many. So you'll see that every single node can only have one inside, and it has a color, right? It's either going to be red or black. And you'll see there's other rules like the root is always black and all common black depth and all that stuff in a moment. So um, just to reiterate, a red black tree is a representation of a 2-foot tree such that it's a binary search tree where nodes are either colored black or red. So it's the same logarithmic performance as a 2-foot tree, although it has a simple implementation because it's only one entry inside of every node. Um, so how you go about doing this is examples of what it looks like. So this is a 2-foot tree with a root of 4, and how you convert that is it's just going to be a black 4, just like that. Whereas a another example that we'll also can look at is if we have a very basic node like we see this 2-foot tree here containing 3 and 5. This is actually one of these two. It's actually either 3 and 5 or 3 and 5, where the 5 is black or the 3 is black. This could have two variations. And although this consequence is there, it really doesn't matter further down the line, because red black trees preserve the in order relationship between different stuff. So this is why, even though this can be the two variations, in principle it doesn't matter, because we still achieve the same computational performance. So one example of this would be if you're going to be putting this in. So what some people do is they draw this out, and then they take a highlighter and then sort of shade it over. Some people do the whole, this is black and this is red. I wouldn't recommend that one. It's probably easier just to color it in, because it's slower to draw the top one and the bottom one. So when it comes to this, you need to sort of understand that you want to go with something that's very efficient when you're drawing this out. And a highlighter is a lot easier to do than, for example, writing other things. I've seen some people do things like, squares and triangles. Again, as long as there's some sort of legend that says, okay, this is what the one is and the other one, that's fine. But I'm 100% sure things will go better for you uh, if you draw it this way and you highlight things. So we go from there. So the next thing we also need to understand is that the colors are there simply to unpack ordering across multiple nodes. Now, remember, everything under the hood is a 2-foot tree, really. So, but how do I understand when, for example, it's on another level, or whether it's in another entry and things like that? That's another story. So, when we have a situation like this, when there's 3 entries, it's very clear. The black one is actually the middle one that we're referring to in all of this. So because this same 2-foot tree is represented in this way, we will always have the situation where the black one is the one that's the parent, and you'd have things like red children. So, but I'll get to the rules in a moment and all that covers all this stuff, and then you'll be able to understand how exactly we go through it. So the properties that sort of define whether it is in fact a red-black tree or not is the following. So we see these 4 rules come up, and I'll show you a trick for determining how to do this very quickly. And hopefully you'll be able to sort of get through these very quickly when you understand all the 4 properties. So the first property is the root is always black. So when I say the root is always black, I mean it. That's how it is. If at any moment in time the root is colored for some reason, we have to change it back to black. And there's a good reason for this, and I touched on it just now, where the parent is always considered to be black in this context. So if the root is not black, this is problematic. So that's the one thing. So that's one. Another one is the external property means that every leaf is black. So in other words, all those little small nulls that we see there are always going to be black. And I would not recommend you draw the leaf nodes, just like I recommended for the AVL trees and the binary search trees. Just draw everything and then don't draw the leaf nodes, but they are there. It matters for when you're doing restructuring and things like that for all the trees, but they're still there. It just makes a lot more sense to just keep it in a sense that we know that every single leaf is going to be black. The third one, of course, the third property is the children of a red node are always black. So if there's a red, uh, you know, when it comes to the children of a red node, so if there's a black parent, the children will be red to reinterpret what's there. So if you have a situation where I have very deep trees and all that that I'm going through, I will always have some sort of idea that I see a red parent, I know there's black children to follow. It's pretty straightforward. So that one's great. And the next one, and I would argue it's probably the most important one, and this is the one that's going to save you for all your red black trees that you're going to be doing, is that all the leaves have the same black depth. So this depth property says whatever path you follow in the tree, no matter where you go, if I count the amount of black nodes in there, they will always be the same. I will have the same black depth. And this is quite easy to pick up whether you're violating this constraint or not. That's why I say this is definitely the very, very, very important one, because we can even see if we check this one first, a lot of the other stuff, it'll solve most of our problems in our red black trees when we're doing this. So the depth property is critical for you to do all the necessary things you need to do. So this is an example of a black tree. Now, what I want to show you is that, okay, the BST ordering is still there. Left, it means less. So 4 is less than 9. That's why it's on the left side. You'll notice that red children always have black children. Red children have black children. That's fine. So that's the other property. All the leaf nodes are all black. You can see that. So that's the one thing. And the other thing that I wanted to highlight is when we follow the different paths, we say if we go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, we will always have common black depth no matter what path, what branch we follow in the tree and all that. It must be that I have that. That's why I say the common the depth property is like that. And that's just we can do it. And I'll show you now that on the right side you'll notice that 15 is black. And that's as a result of a recolor event, or there's a few things that can allow this to do this. So what you'll see is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Notice that the reason why 15 is black in this context is so that we preserve the common depth property. So the common black depth property. And so I know a common assumption is, but Prof, each of the levels mean they're the same color. It's not like that. So you don't alternate between red and black. That's also another misconception. Remember, those 4 properties that I just highlighted there is the primary reason why this is there. So you'll see there's going to be different things that can happen. There can be restructures, there can be recolors, events and stuff like that. So a black parent can have black children, but a red parent cannot have red children. That's correct. So this condition where a red parent has a red child is called double red, and we need to fix it. So that's one of the things we can do that. So we can go from there. So can you please explain how 4, 6, and 7 is still 3 black depth? Okay, let me do that again. So you're saying for 4, 6, 7. So 1, here's a black one, so that's +1. I reach the red, nothing. Reach there, +1. Reach there, nothing. Reach there, +1. Because remember, a branch, that's one branch that I've got there, right? The path I follow from the leaf all the way to the root, right? So if I count the black nodes, there's 1, 2, 3. If I take, let's say I take a different branch. This one, that's +1. So I go 1, 2, 3. Now, because this, you'll see that it's a different branch from, because it branches, it splits at 7. When I'm counting all of this, when I am including in the leaf nodes and everything like that, you'll see no matter what branch I follow in all of this, I will always have common black depth. And if I don't, I need to do something about it. So you'll see that those properties are there so that I know when to do a recolor or restructure. And I'll show you in a moment how that happens. So does that make sense with common black depth? It's still going to be 3 because of the different branch. Can I get a thumbs up for that? Okay. So so when it comes to this, we also need to understand that when I do this, I can also prove that the height of this red black tree is going to be logarithmic. And what you'll see is that by the way we prove this is that the red black tree is at most twice the height of an associated 2-foot tree, which makes it nice and easy to prove. So you can then go on from there and beyond. So the fact that we already proved that a 2-foot tree is logarithmic. If we can then prove that the height of the associated is exactly the MERD version of that in a different format, we can then prove that it's also logarithmic by induction. So the next thing we also need to say is that when it comes to insertion and removal, we need to preserve the properties. So like any other binary search tree, the first thing we always do is a search, right? We do the search to find out where we're going to insert. It's the same with a 2-foot tree. We search, and wherever we end up, that's where we're inserting it. It's any tree for that matter. So no matter whether it's a multi-way search tree or a binary search tree, the search happens first to determine where I'm putting it. And only when the search terminates is exactly where you're going to be inserting it. So in the example of a 2-foot tree, when I terminate, wherever the node is that I terminate, that's where I'm going to insert, and that determines where exactly in the grand scheme of things I am. So please do keep that in mind. And we always want to preserve the properties. And more importantly, as I said before, we want to ensure that we have a situation where, our internal property where we have a situation where if a red child has children, it must be black. That's the idea. So what we have is, to sort of recognize what this looks like is a double red. So that's the sort of violating constraint. A double red is what's created. And this always requires some sort of reorganization of the tree. And the one thing I want to highlight at the stage is that when we insert into a red-black tree, it's always red. So it's going to be red going in. So we know how to get to the where. So we know exactly this is the spot I'm going to put it. The next thing we need to know is that, okay, great, I know where it's going to go. The next question that typically gets asked is, okay, what color is the one I'm putting in? The color of the node that I'm putting in is always going to be red. And once I put in this red node, I then look at the tree and then I fix things. That's when I do my rebalancing or recoloring or anything like that. So an example of what this looks like is, in this case, you'll see that we're adding the node 4. So you'll notice that 4 is the right child of 3, because when you do a search, it ends up being there by, as you see, by Z. And once I place it in there, I have this red node over there having black children. Now, what you'll see is this condition where this double red takes place is actually based on the uncle or aunt, the parent sibling. And, when we look there, that's where we're going to determine whether it's going to be a restructure or it's going to be a recolor, right? And, what I want to say, and before I show you the slides and all that, what I want to say is if this uncle or aunt, if they are red, that's going to result in a recolor. And then, for example, if they're black, that's going to be a restructure. So What I also need to highlight is that, you know, there's a reason why this remedying of the double red is different, because even if you have if you do the wrong thing, you'll see that you don't fix anything. That's why it's very important that you do the right thing, and I'll repeat the rules in a moment. So the cases that we see for a double red is if the parent sibling, that's why I say it's easier just to refer to them as an uncle or aunt. If they are black, this means we're going to restructure, right? This is the equivalent of an AVL tree trinode restructure. It's exactly the same, right? The restructure is probably the easy one because it's like you're pretending it's an AVL tree and you're doing the restructure. And the things like the rotations like single left, single right, double right, all apply. Because in the case of the parent sibling or W being black, this is the equivalent of an incorrect placement of a fur node. So we want to fix this in some way, and that's why we do a restructure. So this looks like the following. Now you'll notice I'll do my check. I see there's a double red there. I look at the parent sibling. You can see that they're clearly black. And because of this, I'm going to do some sort of restructure. And when it comes to this restructure that's taking place, what I want to say is that we need to fix it in some other way. So the fixing happens, and we look at what is the problematic case that we're dealing with here. So when I look at the parent, sibling, and all that, I'm going to do some sort of restructure. The next question is, what sort of restructure? And what I'm going to show you is, I told you there's 4 different options on the table. There's single rotation left, single rotation right, double rotation left, double rotation. And what this looks like is, I'll show I think I did put a slide in for all the potential, configurations and how they end up. Let me first talk about if the parent sibling is red. If the parent sibling is red, this is the equivalent of an overflow in a 2-4 tree. This is a fundamental recolor operation. And the best way to sort of do this is when we have if I have a situation like this, is how I fix this is I look at the parent and I look at the parent's parent, and that's how I'm going to determine what gets recolored. And I'll show you in a moment now how that works. So I look at the grandparent in this particular context to determine how I'm going to do this. So how I do this is the equivalent of you taking this, and remember this is how I recognize it. I have my double red, and when I look at the parent sibling, it's always going to be red, and that's going to trigger a recolor event, right? And how we look at it, and I told you I'm going to look at consult the parent, grandparent, and what's going to happen is the following. We're going to actually look at it from the grandparent's point of view, and we're going to ensure that the children of the grandparent get a recolor to fix this, right? So let's actually go into the minutia of this restructuring and recoloring. So when a restructure happens, we're actually getting the following happen. We're remedying a situation where a parent red node has a double red. When the parent red node has a black sibling, it is the equivalent of restoring a replacement of a foreign node, and it's fundamentally there to restore the internal property. And what I want to show you is when we count all of this, and I want to show you that even if we don't have any black leaves in place, it does impact things, because when I go over here, we can see that I have 2 black depth, whereas when I go this way, I only have 1. And that's one of the things we always see in this condition. And when the other condition, we'll see that when it comes to double red, that's typically required of a recolor. What you'll see is in here it's not as clear that's happening. And that's another thing that you can use to see if things are going wrong. So what we see is the following, right? This example over here, and this is the most ugliest version, I chose it on purpose, is that this is a double rotation. So we have a situation where that's going to go up, that's going to be the right child over there, and what we're going to see is the following. The 6 is going to be the parent, it's going to be a red child, and when we do the restructure, no matter what restructure we do, it's going to be black parent, red children. Whether it's a single left, single right, double left, double right, we're going to have black parent, red children. And what we also need to understand is that in principle, a restructure does nothing in terms of its 2-4 tree representation. You will see that this version looks like that, this version looks like that. So ironically, in terms of the 2-4 tree representation, we don't see any difference whatsoever. But we do the restructure because we have a situation that down the line, this is inefficient. That's why I told you that you can represent it in 2 ways. And the only difference is that the left version of this, in this example, is inefficient further down the line, whereas the right one is more efficient. And this is one of the consequences of doing this in representing the design research tree. So you can convert any red black tree into an AVL tree, and you can convert any AVL tree into a sorry, not AVL tree, a 2-4 tree into a red black tree. So the relationship is between the 2-4 tree and a red black tree, and we can go from there. Can you convert an AVL tree in a 2-4 tree? Yes, there is a way of doing that. You know, most of the time, you can think about it in terms of, aside from the efficient way of doing it, you can literally just offload every single one of the entries inside of a 2-4 tree and then go on from there. But 2-4 trees and red-black trees is very easy to convert from one to the other. Okay. So this is what all the combinations look like. So this is we can see here that this double rotation over here, the 4 is going to go up, and the 4 is going to go up. And what we see is they all end up looking like this. And as I said before, black parent, red children. That's what they all end up being. So no matter what single rotation, double rotation you're doing, it's always going to end up like this. So in many ways, it's actually quite simple, because if you understand how an AVL tree works, you understand how this is going to end up. And if you understand the rule that the parent is always going to be black and the children are going to be red, you'll always know how to fix this. So those double reds will always be fixed without any problems, because when the restructure happens, the parent sibling, in terms of the context for the condition that's required for a restructure, you'll always know how to do it, because it's the equivalent of an AVL tree. So an AVL tree trinode restructure. Recoloring. So as I said before, it's the equivalent of a five node split or an overflow. And the one thing that I want to highlight is that just like 2-4 tree, when the third node goes up and that split happens, it can actually propagate into problems further down the line. So when the third node goes up, we can see that, oh, okay, it can cause problems, because if this one can then cause an overflow, and then it can cause overflows worst case until we reach the root all the way. And that's very much a possibility. So just because this is the equivalent of that, a recolor can result in other things happening, like other restructures or other recolors that can take place. So just keep that in mind. So how does a recolor happen? Well, as I said before, how we fix this is we consult the parent and the grandparent. And what happens is the grandparent becomes the, when it comes to the coloring operation, you'll see that the grandparent becomes red and the children become black. So the easiest way to represent this is I'm going to go into the grandparent, flip the color, and then make its children, those particular examples. So what's going to happen here is that, if it comes to this example where I'm gonna look at the grandparent's color is gonna change as well as the children. I do this in order to fix the common black depth property. When it comes to you making sure that everything goes well, sorry, the internal property works well just fine. So I know that the 4 is going up here, but you know, if you were to have the equivalent representation here, and by the way, I told you take the one that goes up. So if we look at these two variants, and we see that this is what's going to happen. This is the equivalent of this taking place because of that exact example. We're doing this so that we understand that, okay, as it stands, I know that I'm specifically need to recolor so that I comply with everything else. Now notice the black is not black here. So once I do this recolor, because remember this can change things there, this immediately is going to turn black afterwards because I need to make sure that it complies with the root property. So what's going to happen is if the grandparent is indeed the root like we see here, this right afterwards is going to turn immediately black again. So we're going to have a situation where now 4 is black, and because 4 is black, when we do our black depth calculation, we're going to count 1, 2, 1, 2, and we're going to see that it does fix things because when the root is black, it doesn't affect black depth in that way. So the one example, okay, that's a good question. So let's say for argument's sake, I didn't do this and I just changed red to black. What I want to show you is that it doesn't fix things down the line. So because we're increasing our black depth on this side, we're not really, it impacts things on the right branch, but it doesn't, I have a vacuum on the left. The reason why we do the recolor is to prevent this vacuum from occurring where it doesn't violate my common black depth property accordingly. And that's the fundamental reason why we do this recoloring, so that we fix things inside of the actual red-black tree so that it works accordingly. So, when it comes to the algorithm for doing this, as I mentioned before, we search, insert, it's a red node. Once we do this, we then check to see if there's a double red condition. If, for example, if there is a double red, we keep looping until we're done, because potentially this can propagate all the way up. And then we have the other condition taking place where I need to check for my parent sibling. If the parent sibling is black, I need to do a restructure. If the parent sibling is red, I need to do a recolor. So this is the algorithm that you follow when it comes to doing the red-black tree insertions. And as long as you keep doing this, you'll be fine. So when we analyze this from a big O notation, because we have logarithmic height, a search is logarithmic, and step 2 is constant time. And then of course, because step 3 is logarithmic, because we're doing log n amount of recolors all the way, each taking constant time, and at most one restructure taking constant time. So you will notice that the restructure fixes things, there's nothing that follows. Whereas a recolor can result in other things happening down the line. Because of this fact, we have a situation where red-black trees take overlog time for insertion. Deletion. One of the things that I want to highlight is that because it's a binary search tree, we're going to follow the same strategy we did for deletion. We need, once we remove that particular entry, we need to check for those. So if the properties are violated, we then need to do things like reorganizing the tree itself. So in this case, we see, let's say if we delete 8, what we will see is that we have this example where there's this notion of a double black taking place. And the idea is when we see the situation, you know, the internal property causes issues. Now, I know this is the one where people are like, what just happened? Now, that important rule that I was speaking about comes into play. So we see that if we count 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. That is why we need to fix it. Because the when we count our common black depth, when we look at the common black depth, we see that it doesn't have common black depth, and that's how we need to fix it. The reason why we do this is so that we do fix it. And how we fix it is there's three cases, right? The first one is um, when it comes to this, I have a situation where I analyze what the remaining parts look like. So if and you'll see that specifically when we label all this stuff, we need to understand. Okay, great. I need to fix this. How do I fix it? There's three ways it can. So if Y is black and it has a red child, we do a restructure that's equivalent to a transfer, and we're done. If Y is black and its children are both black, we're doing a recolor. So this is the equivalent of a fusion operation. And the fusion operation can propagate up the double black violation. If Y is red, we just do an adjustment equivalent to choosing a different representation of the three node, after which case 1 and case 2 applies. So what we see here is that we need to take into consideration all of these parts. So how we fix this is very much dependent on when we remove what's left behind. So what I want to say is, in a situation like like this, normally your gut feeling is, okay, great, that's what I need to do. So can anyone tell me what is their gut feeling for what they need to do for this example? So your gut feeling is a restructure, right? So let's see if that becomes. Remember, the rule is this is going to be a. I'm going to have a black 4, and I'm going to have red children. So I'm going to have a. And then if I draw my leaf nodes, just in case, remember you don't need to draw the leaf nodes. That should be just fine. So I then look at it and I say, do I have common black depth? If I count 1, 2, 1, 2, 1, 2, 1, 2. What you'll notice is it has common black depth. And what you'll see is your intuition is correct. When it comes to this restructure that's taking place, when it comes to what we're dealing with, the same rule applies. And I know that sometimes looking at that three cases looks very weird and all of that, but most of the time you'll know what you need to do. And your intuition that you typically want to do is typically saying, well, okay, great, a restructure fixes things one time, you're done. Now, if we just took this and said, well, okay, great, let's recolor 3. And if we recolor 3, what you'll notice is that, let's say, for some reason, we just took that and made it red. What we'll be doing is we're introducing a here. And because remember, if we did this double red, how would we fix it, right? If we have a double red, I would then consult the parent sibling, and guess what? The 4 is going to go up anyway. So what I want to show you is that a lot of the times there's things that go further away from what you're trying to achieve, and things that are sort of making your life a little bit more difficult down the line. And that's the reason why. The reason why these cases are in place and all that is to make sure that you solve the problem in a shorter period of time. And by the way, this is the fundamental basis for all the other examples as well. So, for example, if I have a situation where, naturally, I'm just going to assume that, okay, great, well, I have all these rules, I have everything in place, and all that, in there. The properties are there to make your life easier, not more difficult. That's the idea. So please keep that in mind. And what you'll see is if you're going down a rabbit hole where things are not going well all the way, and you probably made a mistake, what you need to see is check your common black depth. Where did I lose things? Where did I lose the plot? And chances are you'll find out immediately where things went wrong, and you can adjust and you can pivot and move from that point onwards from where you made the mistake. So what I'm going to do is I'm going to first of all show what this looks like, the red black tree reorganization and all the different examples, the equivalent versions of that in a 2-foot tree. So for example, the red black tree action of restructuring is the equivalent of a changing of a 4-node representation, because we end up with the double red being removed. Recoloring is the equivalent of a split, where the red is moved, double red is moved or propagated up. From a deletion point of view, we can have a restructure that's the equivalent of a transfer because the double black is removed. Recoloring is fusion because the double black is removed or propagated up. And an adjustment is the change of a 3-node representation that can have restructuring or recoloring that follows. So as I said before, you'll see even if some weird things happen, you'll end up doing what you need to do by keep doing your checks for the properties. And you know your gut feeling is normally right, and you can always check what the outcome is there to see how it goes if you don't understand the cases. Okay. Now, what I'm going to do is I'm first going to get all the content out of the way. So I'm going to go immediately on to the next lecture. And then once I'm done with the next lecture, I'm just going to go and do many examples as much as time as I have left. So and tomorrow I'll keep going with that. And as I said on Thursday, I'll keep doing more revision, and I'll show you some tips for how to actually answer the some of the exam questions um, in terms of expectations, as well as what sort of questions you're going to be getting. I am going to be uploading last year's exam to help you practice for your exam as well. And on Thursday, I'll see if I can just select a few questions that we can then go and do, and I'll show you how to make sure that you don't make any mistakes for some of the key sort of linchpin questions that you typically find in the exam. And what you'll see is it's fairly easy or straightforward to see what to expect. And of course, you don't want to lose a lot of the easy questions that you would get easy marks for. And trees are easy marks. If you don't believe me, a lot of people, if you can just do the trees, you need to understand that just the trees alone is the AVL tree, 2-foot tree, and the red black tree is a quarter of your exam. And I mean, if you think, sorry, not a quarter, it's actually a third. A third of your exam is just that. And you know, you can go from there. So yeah, the next step is let's get through the graph stuff, and then we go from there. So what I also want to say is that once we do the graphs and we cover all the bases, that's the content for the semester. So what I want to highlight here is the graph basics and all that in terms of how to traverse a graph and all that. is very useful for your career moving forward if you're going to be doing other stuff as well. So um, in terms of the mark allocation for graphs, well, I'll talk about mark allocation all that on Thursday of the exam, and I'll give you a nice breakdown for what the marks look like for the exam in terms of how many marks for this, how many marks for that, just so that I don't take any more time today on that. I'll cover that on Thursday, and then let's jump straight into the content for graphs. So when it comes to a graph, if you haven't had you had a graph in your mini project, and normally you go out and you do your homework and sort of see that, okay, great, a graph is the following. I have vertices, and the idea is these vertices or nodes have some sort of relationship or connection with others. So this is typically referred to as edges. So the nodes themselves are vertices, so that we have there, and the idea is that when we look at these nodes or edges and nodes and edges, I like referring to these as nodes because it's easier. So they have either they're connected or they're not, and what you'll see is that you can, a graph is so interesting is that you can actually represent many, many, many problems in the form of a graph. And a graph is probably one of the best ways of achieving abstraction that's scalable for many problems in many ways. In fact, graphs are the fundamental backbone for one of the key linchpins in AI. A neural network is a graph. The only difference is it's a structured graph such that there's specific nodes, and the idea is you're building these edges in such a way that this these nodes have connections. We have input nodes, and we have the output node or the target variable itself, and you're applying certain algorithms on this graph in order to do this. So, for example, when you're training, you're doing a loss minimization function like backpropagation and all that, where we're trying to understand how this input maps to that output. Backpropagation adjusts all the weights of the edges in between each of these nodes in order to achieve what it needs to achieve. So a multi-layer perceptron is actually based fundamentally on this graph. And I would probably be doing an injustice if I didn't do this graph. And you're probably wondering why do we have to do graphs? Because I think it's important. And one of the things you also need to see is that it's used in many, many, many other places. And instead of just leaving it on sort of in the mini project, I thought we'll go through it and add and go in a little bit more depth, so that you just didn't do it for the mini project, and you actually understand what's happening. Okay, so graph is a pair of vertices and edges. So we have all these vertices and edges and a collection of them, where we have a collection of nodes and a collection of edges. That's what our graph is. But what we can also see is that graphs can represent many things. So one example of this is vertices, and each node representing an airport, and each of the edges representing distance. In this case, it's mileage. That comes straight from the textbook. So between, for example, certain airports, for example, to go to Los Angeles, going to LAX over there, or any of the other ones. So let's say from Los Angeles to San Francisco, it would take, you can see that the distance is 337 miles to get there. So the idea is that you're representing some, in this case, the problem space is distance and airports, and we want to actually find, okay, great, how far would it take to get from here to there, for example? And you'll notice that there's multiple ways to get there, and there is such a thing as an efficient route to get there and an inefficient route to get there. And what we'll see is that when it comes to finding an efficient route to get there, to do this programmatically is not as simple of, okay, I moved to this node, let me check around and hope for the best and sort of waddle about and hope I get to my destination. It's much better to do a systematic way of getting there, and that's where traversals come from. It's a systematic way to actually traverse this data structure such that we're trying to do something. Now, the two systematic ones that we deal with are in a graph either depth first search or breadth first search. And what you'll see is those two big traversals are actually, and I know it looks like a lot of stuff to come. It's actually not. I just have lots and lots of pictures for each of the different steps, and we can go from there. Um, what's interesting is that when we look at this and we map our problem in this way, if we have an efficient representation of our problem space, we can do many great things. And what's really cool is when we have an efficient representation, we can actually solve the problem fundamentally. And that's exactly what we're trying to achieve here. We're trying to do a very good way of getting to our destination and actually getting to a point where we can immediately solve any potential problems and even future problems that we haven't covered just yet. So our graphs used on the navigation map. Oh, you're talking about like in Google Maps or anything like that? So what happens is we have longitude and latitude in those problems, and then the idea is there's certain points, and when we have nodes that represent it, what we're doing is we're building a root graph, or we're actually computing the spanning tree of that. This will probably make more sense when I get through the terminology in a moment. But what we're doing is we're actually looking and saying, let's actually see what this looks like. These are nodes along the way, and I get to that point where I actually can discover a route, and then I calculate, okay, traversing there and there, and then I can have edges representing different things. So, for example, edges could just be pure distance, or it could be a case of having some sort of computation inferred where I can actually infer time. And how they do this is they factor in congestion and all that. So these edges represent to go from this node to this node, it'll take this amount of time, this amount of time, and all that. And the idea is that I have an overall time and I can calculate it based on kilometers. So that's one way of doing it. And then these times fluctuate. So, by the way, this is the same thing that was used in computer science to be for nodes, where you can say, well, between this node and that node, this is a Foston, let's say it's a 30 megabits per second, whereas this node, for example, is 7 megabits per second. You'll have a bottleneck from communicating between these two, and it'll be 7 megabits per second. And that's why, because when we navigate this, we have to factor in the bottleneck that's taking place at node 2. Now, there's many other problems that I can use to represent it, but this is just a few examples. So we can have two different types of edges. The one is called a directed edge. So in other words, we can go this way, but we can't go that way. And then, of course, an undirected edge where we can go both ways just fine. And of course, this depends on the problem that we're trying to address. And we can have many sort of variations that come from there. So keep that in mind, because normally, if we have directionality in place, it restricts the computable routes that we can take in the graph itself. So directed graphs, all the edges are directed. Undirected, all the edges are undirected. It's not halfway between each of these. And by the way, we typically call a directed graph a digraph. So there's many types of digraphs that we can also use. And directionality is quite interesting, and that's why I put an extra little slot in there that shows all the different sort of variations, all sorts of there's even other algorithms that are relevant to digraphs over there as well. It's used in many places. It's used in from a manufacturing point of view, from a transport point of view, from a networking point of view, from a databases point of view. It's just used everywhere. That's why it's such a flexible abstract data type. And here's some examples from the textbook. Just some terminology. So you'll see that this comes straight from the textbook as well. There's certain things labeled. So for example, you see A is considered a edge, V is considered a node or vertex. and then A, B, D, C, E, F, G are all edges, and they all have a different relationship. In other words, we have this notion of V as a vertex having all these edges, but what we can also say is there's incident edges. In other words, it comes out of V. So A, D, and B are all incident edges of this. And then we can also talk about this having V having a degree of 3. In other words, there are 3 incident edges coming out of V. And then we can also have what we call a cycle. So cycles are, they go, there's some sort of, it comes back to where it was. And then we can have what we call a self loop that's taking place. And, and then the other thing, of course, we can do is if I want to go from U to Y, there are multiple paths I can follow in order to get there. So what I also need to say is there's a path to get there, and if the path is, for example, cyclic, that's another a cycle we can do that. And it's all in the slides right now. I just wanted I thought I'd show you what it looks like, and then we can look at all of this. So we have vertices, and then we have edges, and we can have an incident edge, and then we can also have adjacent vertices. So U is an adjacent vertex of V. In other words, it's opposite across from it. There's an edge separating it. We can also have this notion of a vertex, a degree of a vertex. So X in this case has a degree of 5. 1, 2, 3, 4, 5. There's 5 edges that come out of it. And we can have this notion of parallel edges. So H and I are parallel because they go to the same vertices. And we can have a self loop. In this case, J is a self loop. So that's some of the terminology to get around there. So a path is a sequence of alternating edges and vertices, where I start off with a vertex and I end with a vertex, and each edge is preceded by endpoints or vertices. A simple path is one where all the edges and vertices are unique, whereas any other path is it can repeat some of the stuff along the way. So a P1 is an example of a simple path that goes from Vx to Z, whereas P2 is not a simple path where I'm going, and you can see because W gets repeated, it's not a simple path. So we call the one that's unique a simple path, whereas it's not simple if you're repeating. As I mentioned before, cycles have some sort of cyclic alternating vertices and edges, and each edge is preceded and followed by endpoints, where a simple cycle has unique edges and vertices, and a not simple cycle has repeating ones. So C1 is an example of a simple cycle. So it goes from V, X, Y, W, U, V, whereas C2, in this case, you're being a nice little figure 8, where W is repeated to make it not simple. What's also interesting is that graphs have specific properties. So when we look at the degree of a vertex, it can have at most 2 amounts multiplied by the multiple 2 times the amount of edges. So that's how many we can have. So we can always calculate some sort of relative mapping of how many when it comes to all the vertices and all that. So we can prove this property because when we start counting these particular vertices, we can say, well, okay, great. If I have 2 vertices, I will have, in this case, I'll have a situation where I can't have more edges in this situation. These are the 2 that I've got there. And, we can, so this edge and that vertex matters. And we can always then say, well, okay, great. If there are, let's say I count in this case here, how many, so my degree will always be 1 year. And then when I look at this way here, because there are two, two vertices of the year, my degree of this one is going to be 2. All right, and it's just a fancy way of saying when I count my incident edges, I'm going to have 2 when there's 2 over there. If I have 3, I'm gonna have 3. So that's what we're trying to show here. It's just a fancy way of saying that. It's because every edge, that we see here, is counted so that we can map up to our degree of our vertices. What is the bound of a directed graph? It's a little bit more complicated than that. And we can always see it because if it's directed, I can only traverse once and I can never go back. So we can then have a situation where graph never gets to the edge it came from, and that's also something that we can look at. It can never. So we can have a situation where we get stuck. So let's say there's it all goes to this one. It can never go out of that one as a result of that. So that's what you also want to take into consideration. So n is normally number of vertices, m is the number of edges, and the degree of, like I've shown you now, is the degree of vertex v. Once you've got all that notation in place, you can do the following. So you can see that n, in other words, the amount of vertices is 4, m is the number of edges that we see here that can potentially happen. And what we can see is that the degree of the vertex is 3, and this is where that property came in that said that the degree is typically we can see that the amount of edges, these relationship. So if you look at the degree and the amount of edges, this is it's twice the amount of edges that we have there. So we can see that if we didn't know how many edges there were, the total amount of the highest degree that we can typically have is based on that. So you can keep that in mind. The methods. Typically, we store positions inside of there, and which each store elements, and then we have this notion of what we call an end vertex, which is end vertices is an array of all the vertices of E for the edges, and we have this notion of an opposite. So if we want to refer to the opposite, and then we also ask ourselves, are they adjacent? Is there an edge between them? Can we replace the vertex, and can we replace the edge? So we also have insert vertex, which just simply adds a node. Insert a edge, which just adds an edge, and of course we can remove them as well that we have there. There's some iterator methods like inserted edges. So for one, V, it'll iterate through each of the edges for each of them. Vertices are all the vertices in the graph, and edges are all the edges in the graph. Now we can represent the graph in computer science in there's 3 big ways. So the one is what we call an edge list structure, where we store the vertex object inside of a vertex sequence. So and then each edge object has a sort of origin and a destination, and then we can go there. So what it looks like is we have this graph over here as a sequence of these particular nodes and edges. So you can see that we always store the references of the origin, the element reference, and we have typically we store cost and stuff in there, and then we have the source and the destination that are stored inside of the edge object, whereas the vertex just refers to um, the thing that we have there. So we can see all these references of source and destination by storing it as 2 sequences. So the one is more for the vertices and the other sequence is more for the edges. That's how we do that. Now you can see this one is conceptually, it's not so great, but it is quite nice in some ways. But it depends on whether you're going to be operating more on edges or vertices for choosing one of the 3 formats. The other format is an adjacency list structure, which is more conceptually simpler, where we look at it in terms of incident edges coming out of a vertex. So we look at it in terms of the following, where we store it in the following way. We see that specifically we store what are all the adjacent nodes for each and every one of them. So how we store something like this is we store based on all the edges that come out of one vertex. So in this example here, we see that the vertex in here has reference to, so we can always see, okay, uh, is this if is U connected to V? If it is connected to V, I have a reference to that, so I can see that when I analyze the object inside of the so when I inspect the entry inside, when I inspect the node inside, I can see all the different incident edges that come out of one vertex. And it's probably easier when we look at, and I'll show you the more common representation, which is an adjacency matrix. And it's exactly the same thing as an adjacency list, but just stored as a matrix, where I keep track of all the edges that are the relational mapping between different vertices. And how I do this is I have an example of this matrix that's stored, and for example, I would have an example of, okay, is U, V, and W there, U, V, and W, and then I have a situation where these are all nulls because let's assume there's no self loop, and then I would have a situation that say, well, okay, great. If it's a binary matrix, how do I know that U is connected? So in this case here, this would look like, because U is connected to V, U is connected to V, I would have a 1 there, and I'd have a 1 there. Is U connected to W? No, it's not, so I would have a 0 there. So is V connected to W? Yes, it is. So I would have a situation where this is what the matrix would look like. It would be 0, 1, 0, 1, 0, 1, 0, 1, 0. And the zeros would always be on the diagonal because there's no self loops in this context. And if, for example, we wanted to have weights, so let's say the weights were there. So in this case, you can see the weights are B and A. So whatever the weights for B and A would be, so for example, in this example, one would, instead of being in one, if it's undirected, or sorry, it is, there's no cost or there's no weight on it. If there is a weight, I would have to put the exact measure. So in this case here, V and V and U would be A. So you'd put an A in there, which would be the cost of the edge itself. In other words, what's value is stored there. Instead of storing it as a binary matrix like that, you would actually put the exact value in of what the cost is instead of the 1. And that's an adjacency matrix structure. In the past, in case you're wondering, some of the questions I've asked would be, I give this, give me the, one of these, or the other way around, or I give you a matrix and tell me what the graph looks like. So those are examples on that. And then, of course, traversals on the graph. But that's as far as when it comes to the kind of questions that I would ask. So that's what you should focus on. In terms of the space usage, it's n squared. In most cases, for adjacency matrix, whereas an adjacency list depends on the edges and the vertices. And there's a consequence for choosing each of these three. If you're going to be doing so, here we're sacrificing memory in for performance. So whereas you're, from a, if we're dealing with it, so these are conceptually simpler, just different data structures underneath the hood. But the edge list itself is focusing. If the edges are more important, then we use that approach. If the vertices are more important, we use either adjacency list or adjacency matrix. Um, there's subgraphs as well, where you can have inside of another graph a collection of these. So you can have a situation where this is only the graph and then there's the big graph. So this would be a subgraph of the big graph. And we talk about a spanning subgraph In other words, it has all the spanning subgraph contains all the vertices of G's. In other words, the vertices are covered, but not necessarily the edges. So you can have what we call a spanning subgraph, where all the vertices inside of the big graph are included, but not the edges. So this is an example of a subgraph over there, where if I look at this example here, where these are the ones included, that's a subgraph, whereas this is a spanning subgraph because it doesn't include these edges inside. So that's what we would consider a subgraph. Connectivity, can I reach somewhere? So in other words, is there a connected path to get there? Because sometimes you could just have something like this, where in order to get to this node here, there's no way to get there. This is still a valid graph. It's just there's no edges between this one over here and all the other nodes. So even though it's a graph, connectivity is important as well, because we can have this notion of something not being connected. So if we have the situation where we look at it, we can have many subgraphs inside of them, but whether they're connected or not is another story. So another thing we have is a tree. Now, I like to call them free trees. So a tree inside of a graph, and by the way, as I said before, trees are graphs. They just look weird in this context when we look at it in terms of nodes and edges. Um, A free tree is an undirected graph such that T is connected. In other words, there's edges that go to all the nodes. It has no cycles. And what I want to say is that this definition of a free tree is different from one of a rooted tree. A rooted tree has a starting point. So all the other rooted trees we have, the starting point is always there. Whereas a free tree has no notion of a starting point. So examples of a tree would look like this. So we don't have any cycles. We have all of them connected to one another, and this would be a valid tree in this particular context, a free tree. A forest is a underrated graph without cycles, and there are many trees inside of it. So you know that connected definition. We have multiple trees that are subtrees inside there, and this would be considered a forest. So this is the basic kind of tree. This is another tree, and this is another tree. Collectively, this is referred to as a forest. Just to get some of the terminology out of the way. Then we can have this notion of what we call a spanning tree and a forest. A spanning tree is a connected graph such that the spanning subgraph is in fact a tree. In other words, the subgraph that I get out of it connects to all the vertices that I was looking at, and a spanning tree is not unique unless the graph is a tree. And the reason why I talk about spanning trees is because it's used in many other application domains. We can also have this notion of what we call a spanning forest. Is a spanning subgraph that is a forest inside of that. So this is an example where this is what the graph looks like, and the spanning tree would look like this, where the subgraph that I excluded, these vertices, just so happens because there's no we don't have any example of cycles of all the vertices when I visit them in paths. I can all the paths that come out of this are all unique, and I don't end up being to the other side. That would be considered a spanning tree, and that's where I'm going to leave it off today. Before tomorrow afternoon, I'm going to cover some traversals like the depth first search, breadth first search. I'm going to briefly touch on directed graphs, and then we're going to be wrapping up for the semester. That's it. Enjoy the rest of your day, and everything of the best for all of you as we navigate this last week. Thank you.